Welcome everybody. Today we will complete the lesson from the previous video. The previous video was talking about the nucleophilic substitution of haloganoalkane, and you can find the video in the description box down below. In the previous class, we said that if you have a haloganoalkane, like this guy here that contains a bromine, if it reacts with a nucleophile, like OH, you could have another nucleophile like nitrile or NH3. Okay, it depends on the questions that you were given. So if this halogen reacts with this nucleophile, you will end up with a substitution. This guy in here, the bromine, will be kicked out and replaced by the OH if the nucleophile is OH negative. But the question now, how it's happened? What is the mechanism for this process? So we will introduce you to new types of mechanisms in this reaction. And since we're dealing with the nucleophilic, we can abbreviate it in terms of N letter and substitution in terms of S. So we will take two mechanisms. The first one is called SN1. The second is called SN2. The SN1, as we said, S is for substitution, N is for nucleophilic. It says that the rate of reaction depends only on one material in the reaction, which is this one, which is the haloganoalkane. In other words, it depends only on the concentration of one reactant, which is haloganoalkane. And that's why we can say SN1, because it's only one reactant that it depends on. And the opposite is true for the SN2. We have a nucleophilic substitution SN, but the two here depends on the both concentration of hydroxide or the nucleophile and the concentration of haloganoalkane. So that's actually the reason behind that. So if you were studying the rate of reaction and the kinetics and this stuff, you can say that the concentration in the SN2 depends on both concentrations for reactants, and for the SN1 it depends only on the concentration of haloganoalkane. Let's give you an example of this guy in here. You have a carbon that has 3 methyl groups around, and now my question is, how can we do this process? Let's say you have Cl. Okay. First of all, you have to look at the type of the haloganoalkane. This is the most important step in here in order to determine whether it's SN1 or SN2. So first of all, you look at the structure. You can notice that the carbon that is bonded to the halogen, all right, this guy in here, actually is bonded to 3 alkyl groups in here. All right, and since it's surrounded by 3 alkyl groups, then the structure of haloganoalkane here is tertiary. As it's tertiary, then it will undergo the SN1. So the tertiary likes to be undergone by SN1 mechanism, and it's always for SN1. Okay, what is the mechanism? First of all, you have to show me the partial charges in here. And as we can see, you notice that the chlorine is an electronegative atom. Since it's a halogen, it has a partial negative charge. And for this carbon in here, it's partially positive because, like the most electronegative is a chlorine, and that's why it's partially negative. As a result of this difference in electronegativity, the first step in the SN1 mechanism will be breaking the C halogen bond. I mean, this guy in here, it will be broken. And that's why, how can I represent this breaking? You should put in your mind, you have to draw an arrow in the middle of the bond and then show me that you have a heterolytic cleavage or fission of this bond. It means that the electrons in the bond are completely transferred to the Cl in here. In other words, the bond is broken. And all of these electrons are going back to chlorine. All right. So what will happen to this guy after breaking the bond? You'll notice that this carbon, which is poor, it's positive. 1, it's not a partial charge, it's a positive charge. Okay, and CH3, CH3, and CH3. And you have to put in your mind the breaking of this bond in here actually is a very slow step. And if you're interested in studying the rate of reaction, we are studying this last step because representing a step for studying the rate of reaction. So this is really important and it's related to that. After doing this process, we have the nucleophile. And let's take an example of the beautiful nucleophile that we taught. Let's say hydroxide. As we mentioned before, we could use any nucleophile that we discussed in the previous class, and it's okay. Now we have a beautiful nucleophile. It likes a positive charges, and that's will be a good attack to the carbocation in here. And the product will be a beautiful compound of alcohol, and yeah, it will be like this. And here I have the methyl group. By the way, the structure of alcohol at this point is tertiary alcohol because, you know, like this carbon here is bonded to 3 alkyl groups. What we should know about the SN1, first of all, there will be 2 steps for that. One of them is slow, the first one, which is breaking the bond, and the second one is very fast. All right? And we have another thing. You will have a carbocation. And the carbocation in here is tertiary, and it should be tertiary. You can see that this is a group here, another one. So this is tertiary. And the reason behind the formation of carbocation, like why do we have carbocation? We can notice that once it's tertiary structure, which means that you have a lot of alkyl groups around the carbon. And the carbon itself, the positive one, it doesn't like the positive charges. In the presence of alkyl groups, because it contains a lot of electrons, they can say, hey, beautiful, don't worry, we're beside you. We can help you by filling these electrons. And that's why the carbocation becomes a bit happier as a result of the presence of these alkyl groups. So we can say that we call this a process, by the way, a positive inductive, by the way, this is a keyword, positive inductive effect of what? Of alkyl groups. So the alkyl groups makes the carbocation very happy. And now, guys, let's jump to the second mechanism, which is SN2. First of all, which makes you a bit happy, it's a bit easier than the SN1. And now let's take this beautiful guy in here. You have CH3, CH2, and Cl. So as we can see, if I want to write the display formula of this compound, you can notice that it's just like this. We have hydrogens, hydrogen everywhere. All right, we write them. Okay, never mind. Okay. First of all, I have to check the structure. What is the structure of this halogen-alkane? You can notice that this is the target in here. You can see that we have carbon atom that is bonded directly to the halogen, and this beautiful carbon actually is bonded to only 1 alkyl groups, and the rest are hydrogens. So since it's bonded to 1 alkyl group, then it's considered to be a primary. And by the way, the primary has a story. The first thing that you have to put in your mind at this point here, actually it takes place in only 1 step. And there will be no carbocation. And the reason behind there's no carbocation because the primary carbocation is unstable, okay? And the reason behind, if you look, it's just you have only 1 alkyl group in here. But here you have hydrogen and hydrogen. So the hydrogen doesn't contain electrons. And that's why it makes the positive charge very effective. And that's why there is no need for the carbocation at that point. So what will be the step in here? Okay, so what will be the process? Put in your mind, carbon atom makes only 4 bonds. This guy here is partially positive and this one here is partially negative. The process will come in only 1 step. The nucleophile will attack the carbon that is partially positive, and then heterolytic cleavage or fission will happen. So as we can see, it will come like this. And yeah, this is actually the mechanism. We don't have carbocation. You will have a primary alcohol. It becomes hydrogen. You have OH here, and here we have H's, as you can see. For the SN2 mechanism, which is easier, it's placed in only 1 step, and it's special for primary haloganoalkane. As we can see, let's repeat it again. You have 1 alkyl group in here that is bonded to this carbon. Okay, and the rest are hydrogens, and the hydrogens do not contain electrons, and that's why we cannot make a carbocation, okay? In addition to that, no carbocation at that point, which is way better. And now you'll ask me about, we said that the primary takes place in SN2 and the tertiary takes place in SN1. But what about the secondary? Like you, secondary takes place by both, but it depends on the structure of the haloganoalkane, and there are no more details that you should know about this so far, the A level, but you will take these informations in the university if you dive deep in organic chemistry.